Good morning. Today we will discuss the non-homogeneous case of linear ODE. So, how to find the solution of a non-homogeneous linear ordinary differential equation? When do we call it non-homogeneous? If the right-hand side, that is x, is non-zero function. If it is zero, then we call it as homogeneous. Now, in the previous lecture, we have seen when we have zero right-hand side, then the solution that we have found was the complementary function. Complete solution is equals to CF plus PI. Today we will discuss the concept of PI, the particular integral. So this is a rough sketch of the solution of the differential equation. If the given differential equation of this form, then remember this K1, K2, and K3 are constant coefficient. They are not functions. In fact, constants can be treated as a function of x. Okay. So in that case, when we have right hand side non-zero, then the complete solution will be of this one. Now, just to give you one idea that the right hand side function can be of this form. So these are six popular forms which we will discuss one by one. Okay. In fact, you can define it as a case of five main cases, or in the last case, we have seen that this is only any arbitrary function. These are specific functions. Okay, today we'll just try to cover all these four cases, and the next two cases we'll discuss in the next class. So the working formula for the different cases are as follows. Now, if the right hand side x is e to the power ax, then we will find the particular integral in this way. So this is the case, and this is the proof of the formula. Now, what is f of t? For example, if we have, in fact, this is the case f of t, f of t of y equals to 0. So this is a function of f of t. Now, this ODE can be written as, okay, if you try to write it in this form, so this ordinary differential equation, it can be written as f of t of y equals to x in the short form. Okay. Now, where f of d is the function d to the power n plus k1 d to the power n minus 1 plus k2 d to the power n minus 2 plus dot, 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 and kn. The idea is to write the function in terms of, yes, so ODE, the given ODE f of t times y equals to x. So this is the working formula for the right hand side when x equals to e to the power x. So this will be clear if we discuss one example, some example. Now this rule will be paid, provided f of a non-zero. Because if it is zero, then this rule will fail. So in that case, what we have to do, we need to revise formula. So in that case, we have to write it this form. So we'll take the first order derivative, and in that case, we'll take one extra x in the left hand side of the quantity that is written in here. But if f dash of d is also zero, then again this formula will fail. In that case, we go for the second order derivative. This should be non-zero. So the idea will be explained in this example. So this is the solution. So in order to find the solution of this differential equation, we need to work in this way. So this is t2 plus 6t plus 9y equals to 5 e to the power 3x. So here x is 5 e to the power 3x time, the right hand side. And the function f of d is t square plus 6t plus 9. So if you calculate f of a in place of a equals to 3 here. If you compare it, e to the power ax, this is a standard form. Compare it, a equals to 3, put a equals to 3. Then if you calculate f of 3, this is 3 square plus 6 into 3 plus 9. So you get here 9 plus 9, 18 plus 18. So we have 36. So this is non-zero. Okay. So that means we can apply rule 1 by f of t e to the power ax equals to 1 by f of a e to the power ax. Apply this rule, then, so in this case, we have pi equals to 1 by f of d, f of 5 times e to the power 3x. So this is nothing but, um, so 5 is a constant, so take it out, 1 by f of t e to the power 3x. So this is nothing but 5 times 1 by f of 3 e to the power 3x, because f of 3 is non-zero. So this is nothing but 5 times, this is 36 e to the power 3x. So this is our particular integral. But we want to find out the complementary functions also. Okay. So for this, because it is mentioned to find the solution. Now d square minus, sorry, plus 6d plus 9 equals to 0. So if you write, put d equals to m, to find out the complementary function. Substitute d equals to m, then we have m square plus 6m plus 9 equals to 0. So this is going to be m plus 3 whole square equals to 0. So from here we get m equals to minus 3 comma minus 3. So hence the complementary function c1 to the power, because equality case, so we have to write x into c2, then e to the power minus m1x, so 3x, e to the power mx, m1x or m1 is minus 3. Here m1 and m2 are equal. So this is our complementary function. Hence, thus the complete solution is, because the complete solution will be written in terms of y. So y equals to, we can write c1 plus c2 into x e to the power minus 3x plus, because the formula is cf plus pi. So pi is 5 by 36 into e to the power minus 3x, where don't forget to write c1 and c2 are arbitrary constants. They are integrating constants. So this is how we find out the complete solution if the right hand side is e to the power ax form. So this is for example 2. If we have different functions like this, different differential equation, and I try to find out the solution. So it has the right hand side x is now given as 6 e to the power 3x plus 7 e to the power minus 2x minus logarithm of 2. So this can be, it has three components. Okay. So we'll apply this formula f of t y equals to right hand side. Make it in the standard form and then apply it for each component. So this is for the first component, this is for the second, and this one for the third component. Because 1 is multiplied, so e to the power 0x can be written in place of 1. And here we can see that here f of t is d square minus 6t plus 9. So if you put f of 3, then it becomes 3 square minus 6 times 3 plus 9. So this is 9 minus 18 plus 9. So this becomes 0. Okay. As it is becoming 0, so we go for the derivative f dash of d. What is f dash d? So 2d minus 6. Now if you substitute here f dash of 3, so this is becoming 2 times 3, okay, minus 6. Again it is becoming 0. So what we have to do? We again differentiate. We'll go for the double derivative, second order derivative. F dash of t, this is 2. And f dash, f double dash of 2, 3 is non-zero. So that is why first we take one x outside from here, and then in the next step we take another x, and if double dash 3 is non-zero, so we put it in this here, and this 6 was as a function of the given function. But in these other two components, we can see that f of 3, f of minus a, or f of a is non-zero. So in that case, we directly find out the solution. So this is the pi and this is our cf. Hence, this is our complete solution. So these are your for practice problem. Try to verify them. Okay. These problems I have taken from some other textbook, from different textbooks. So the answers may not be correct, but this is for a rough idea that this can be the answer. So that is why I always write, try to verify the answers. You may get a different answer if you are that if your calculation or steps are correct, then you may get a different answer. But this will give you a rough idea of the possible answer. Now, if you go back and check, the second rule was if the right hand side was a function of x to the power n form. So in that case, our working rule will be first this f of t will be written into 1 plus phi of t form. Okay, and then we will try to take the inverse so that it will become easier to calculate. If you remember, the infinite series of expansion, infinite series, binomial expansion of the infinite series. So these are the few cases that will be used. So we'll discuss this with the example. So here f of t is our d square plus t. Okay. Now if you write 1 by, remember, if you try to put for CF, let us write auxiliary equation. What is it? M square minus plus m equals to 0. So this is nothing but m plus 1 equals to 0. So we can write from here m equals to 0 and m equals to minus 1. So the complementary function can be written as c1 e to the power 0 into x plus c2 e to the power minus 1 into x. So this is nothing but c1 plus c2 e to the power minus x. Let us call it 1. Now we have to find out the pi. Because x is now x to the power n form, the right hand side. Okay, and the working formula is one by f of d x to the power n is nothing but 1 plus phi of t inverse x to the power n. Okay, so why we want to write this, because the reason will within some few iterations within, or it can be written as plus minus whenever it is needed. We can write it plus or it is minus. So now if you write it 1 by f of t, here what is given? 1 by t square plus t. So here it is actually, or if you take t outside, so this is becoming 1 plus t. Okay. So here, from here you can write 1 by t times 1 plus, this is phi d. Okay, this is d. And if you take inverse, so if you apply this formula, the pi is 1 by f of t, x to the power, what was that? 2x, x square plus our given formula, x square plus 2x plus 4. Okay. So if you do this, what you will get? In place of f of d, you can write d 1 plus d x square plus 2x plus 4. Now here we can get 1 by d, 1 plus d whole to the power minus 1 x square plus 2x plus 4. So from here you will get 1 by d, 1, this is minus d plus d square, again this is minus d cube, so plus minus it will become plus d to the power 4, become minus and so on. And here you have x square plus 2x plus 4. Now if you remember d of x to the power x square plus 2x plus 4, what is it? D dx of x square plus 2x plus 4. So this will become 2x plus 2 plus 0. If you write d2 of this one, x square plus 2x plus 4, so this is nothing but we have to derivative this quantity again. Okay, we have to find out the derivative of this quantity again. So here we get 2 plus 0 again, that is 2. Now if you take d cube x square plus 2x plus 4, so this is nothing but 0. Similarly for d4 you will have 0, all other terms will be 0. So here you can try to write. Okay. So from d3 onwards everything will be 0, but for d2 we will have this 2. So this is 1 by t. So 1 into this part, so x square plus 2x plus 4, then d of this x square plus 2x plus 4 plus d2 of x square plus 2x plus 4 plus 0. Everything else is 0 here. Okay. So you have here 1 by t x square plus 2x plus 4. So for this one, how much it will be? Minus 2x minus 2. And for this one, we will have plus 2. So this minus 2x gets cancelled. These two gets cancelled. So finally we have 1 by d of x square plus 4. But again, 1 by d we know integration x square plus 4 into dx, which is nothing but x cube by 3 plus 4 times x. Here we will not include any uh, constant because this is a particular solution, and since it is a two or second order second order differential equation, it will have only two arbitrary constant, and these two constants we have already included in the complementary function. So the particular integral will be without any constant. So that is why we need to write the solution in this form. Hence the solution, complete solution. Y equals to Cf plus Pi, which is nothing but C1 plus C2 into e to the power minus x plus Pi we have calculated here x cube by 3 plus 4x. So that's our final answer. Similarly, we can calculate for this example 2, that is, so first you have to calculate the, so right hand side is x to the power 4, that is x equals to x to the power n form, the right hand side. Okay. So in that case, first we have to calculate the CF. Since the roots are different, real roots are different, and it has complex roots also. So that is why we write down the complementary function, and then we try to find out the particular solution. For calculating the pi, we just need to write as a function. So here we have this 1 plus phi of t form. Now we will take it in the inverse, and then we'll use the infinite series expansion. Okay. The reason is that we want to make it 0. After some terms, everything will be 0, so that we will get the particular integral. So here we get the particular integral, and we can write down the, so together this CF complete solution is CF plus PI. CF is calculated here and PI in the next page. Now for another different problem, we have this kind of particular integral formula. So 2 can be written as a x to the power n function also. Since it is the right hand side is constant, 2 times x to the power 0 form. So this is our x equals to x to the power n form, right hand side. So try to verify. Same example, similar example. Also verify this fourth example. Similarly, you also try to verify this fifth example. And after verifying this fifth example, try to solve this example. It's practice problems. Now we go to the third rule of finding pi. When the right hand side is of this form, either it is a sine ax or cosine ax, provided if f of minus a square is non-zero, then we will apply this formula. Similarly, for cosine function, we will have this formula. But if f of minus a square equals to 0, then the above rule fails. Then we have to modify in the similar manner that we have discussed for e to the power ax form. So 1x will be taken on the left hand side and minus a square will be substituted in the derivative. Similarly, for this case also, if the first order derivative evaluated at minus a square equals to 0, then we will have 1x square will be taken. Okay, and this way we will proceed. So, for example, 1, you take this. So, this is a complementary function. Since these are a complex root, so we will have this as a e to the power 0x plus a cos 2x plus b sine 2x. Okay. And now we want to find out f of d equals to d square plus 4. Okay. And right hand side we can see this cosine ax, cosine 2x. So if you write f of minus d 2 square, so this is becoming minus 2 square plus 4. So this is 0. So we find out f test of d. This is 2d. And we will evaluate again f test of minus 2 square. So this is nothing but 2 times minus 2 square. So this is 2 times minus 4. So this is becoming minus 8. Okay. So this is non-zero. So when it is non-zero, we can apply the formula. Or in fact, yeah. So for this f of t, 1 by f of t. So this is pi. Here the pi is calculated in this form. Sine, not sine. This is cosine 2x. Since f of minus 2 square is 0, so we'll take 1 outside, x outside, then f dash of t cosine 2x, and this is nothing but x into 1 by 2d into cosine 2x. So if you expand this, you will get, so pi equals to this one, x by 2 into 1 by d cosine 2x. So this is nothing but x by 2 integration cosine 2x into dx. Okay. So this is again x by 4 sine 2x We will not include c because we have included two arbitrary constant already there. So because of this, we will have this solution. So the complete solution is given by this equation. So for example 2, try to verify this result. Now in this case, you will see that after here, if you substitute here minus 1, okay, 1, f of a, f of 1 is 0 here. So that is why we will take the derivative and we will substitute this value. Okay. But some other problem, we will substitute this value in place of t square. This d can be written as d square minus d square into d. So here we have substituted minus a square because 1 is there. 1x, that means minus 1 square will be there. So because of that, we have substituted here and we have modified this function as this form. So try to verify these results also. Similarly, for this function also try to verify. Actually, all these are not so difficult. Just apply the formula in proper way. If you do that, then you will get the final solution. They may be lengthy, but they are not difficult. Just follow the structure and the rules and the steps. That's it. So for your practice problem, try to verify. Now, last topic today, we will discuss if the right hand side, that is x function, is of this form. E to the power ax is multiplied and together we have some other function of x. Okay. So when we have this kind of functions on the right hand side, then the particular integral will be calculated of this form. So in place of d, we'll substitute d plus a, and that e power ax will be taken on the they will be taken on the left side of the quantity. So let us try to calculate. So this is example 1. Try to go through it. So this is the function is e to the power ax into phi of x form. So apply rule 4. So here in place of d we'll substitute d plus, remember a is 2 here. So ax, that means a plus 2, d plus 2. Substitute it and then evaluate, simplify. So if you simplify this, then this becomes of this form. So try to verify. Similarly, this is again e to the power ax into phi of x form. Here phi x is the sin x. So we apply this formula in place of, so that's our working formula. This rule 4 will be used to solve these equations. Okay. So apply this formula here. In this case, in place of t, we will substitute t plus a, and then we will proceed as usual. We have been doing previously. So if we get sometimes f of t equals to 0, then we will go for the f test of t, and so that it becomes negative. Unless the denominator becomes negative, we cannot proceed. So we have to be careful about this case. Whenever we write 1 by f of t or 1 by f of a, in place not t, 1 by f of a, in fact from here we will get, as long as it is non-zero, we can proceed. If it is 0, then we have to go for the next derivative. So now we can look at the example. So again, try to verify this example. Similarly, this is again e to the power ax times phi of x form. So here we will substitute again d plus a, and then we will proceed as usual. So verify these results. Similarly, go through it. So for the fifth example, try to verify. Remember, we are having three functions, but again we can consider it as a e to the power ax times phi of x. The phi of x is the x square into sine 2x. So that's our function. Like I said, the problem is not difficult. Okay, the methodology is not difficult. Only thing it is, we have to be careful while doing the calculations. It may be a lengthy calculation, but it is not a difficult one. So try to verify these results also. And then for practice problem, try to solve these problems. So I will stop here today, and in the next class we will discuss case 4 and case 5 and 6 and other important issues.